Technological achievements of modern America rest firmly on our understanding of the world of atoms. In fact, if the world of atoms is not real, it would seem that American industry is built on an illusion. But perhaps you want to remind me at this time that the world of atoms is a world of theory. If you are a hard-boiled realist, you may have a deep instinctive distrust of theory. You may say, is it not true that the world of atoms is an imaginary world dreamed up by scientists to explain chemical experiments and chemical processes? No matter how useful these ideas are, how can you be sure that atoms are real in the same sense that chairs, trees, and houses are real? Isn't it true that in many cases there are several theories that fit the same facts? Haven't the scientists again and again had to change their theories? Didn't Einstein's idea of relativity upset a well-established and useful theory of motion? Did it not even upset our ideas of time and space? How then can we be sure that the theory of atoms will not be swept away by some future scientific revolution? These are hard questions, though some of them have obvious answers. To be sure, the world of atoms is a world of scientific theory, and scientific theories do change constantly. But the point to remember is this. When a fundamental theory with a wide range of applications is replaced, the new theory must explain all the facts and relations explained by the old theory. Therefore, it inevitably resembles the old theory in many respects. And by our present theory of atoms, we are able to tie together a vast quantity of facts. Therefore, we can be sure that any new theory that takes its place must preserve the truly essential features of our present one. So as science makes new discoveries about the structure of matter, we can expect subtle modifications of our present theories. But the abandonment of atoms is unthinkable. That would make nonsense of modern physics and chemistry. Mature science never destroys itself. It may change its clothes, but not its skeleton, and the atomic idea is part of its skeleton. Moreover, we have certain crucial types of experiment that point so directly toward the reality of atoms that the evidence seems truly overwhelming. I want to show you several direct proofs of atomic and molecular reality. First of all, there's the Brownian motion. You have to use this to see it. Under the lenses of this microscope are fine particles of a mineral suspended in water, nothing else. The particles do not sit still. They perform an unceasing irregular motion, as if they were alive. They are not alive. All such particles execute this Brownian motion if they are small enough. Take a look. You see particles of various sizes swimming in the water and drifting about. Look carefully at the smaller particles. They move somewhat irregularly and sometimes change their courses. They move because they are small enough to share in the general temperature agitation of the water molecules that surround them. They are jostled by the invisible water molecules, just as a ship at sea is jostled by the waves about it. The movement of a large ship is much less violent than that of a small boat. So here, the large particles are less active. This is thermal agitation made visible. These particles are not molecules, they're bits of powder. But their motion proves the existence of a concealed thermal agitation. They give striking confirmation of the atomic conception of the nature of matter and heat. But I can do better than this. For example, today it is a commonplace matter to record individual events in the atomic world. This recording is made easy by the existence of radioactive atoms, atoms that spontaneously explode from time to time. As they explode, such atoms throw off high-speed projectiles. There are several kinds, but one variety of these projectiles is the alpha particle. This is an atom of helium that carries a double electrical charge. You see, when an alpha particle is ejected into the air by a radioactive atom, it passes through thousands of molecules and knocks chips out of many of them. When a molecule is struck by a flying alpha particle, it is commonly broken into two parts, one carrying a positive charge and the other negative. These charged particles, fragments of atoms or molecules, are called ions. The process by which they are formed is called ionization. Now one can observe the production of ions by alpha particles or other kinds of particles, for that matter, in several ways. The simplest is to make use of the fact that any gas containing an appreciable number of ions is a temporary electrical conductor. You can send a pulse of electrical current through it, amplify the pulse, and use it to trigger off a loudspeaker. This is the principle of the Geiger counter, which is used by prospectors hunting for uranium and for many other purposes. This instrument makes a clicking noise when it is in the presence of radioactive rays or the ever-present stray cosmic rays. Each of these clicks records an individual atomic explosion producing an alpha ray or a stray cosmic ray. As the ray enters the instrument, it triggers off a pulse of current, which clicks in the loudspeaker. Here's a block of uranium. If I bring this close to the mouth of the Geiger counter, it goes crazy under the influence of the alpha particles which are constantly being emitted from the surface of the uranium. These clicks mean flying particles moving with enormous speed, particles ejected by the spontaneous explosion of atoms of uranium. Notice, you can't see an individual uranium atom or a flying alpha particle, but you can hear one. Or do you object to saying that you have heard my voice when it comes to you over a telephone wire or by the way of the unspeakable complications of a television recording? This is pretty impressive proof of the reality of atoms, but we can do better. We can see the track made by a flying alpha particle. As these particles fly through the air, each leaves behind it a trail or track of positive and negative ions. These ions are as invisible in an ordinary microscope as the alpha particles themselves, as invisible as all individual molecules, atoms, or subatomic fragments. But there are ways to convert the invisible trail into a visible one. One way, developed by C.T.R. Wilson, is to allow the ion trails to form in chilled, moist air. For example, let me blow on this piece of cold, dry ice. You see that the moisture of my breath forms a cloud when it's chilled. The chilling creates a fog by condensing water vapor into a multitude of tiny, visible drops of water. If there are ions present in such moist air, the water drops condense on them first. If these ions are distributed along the trail left by an alpha particle, the water droplets form a line or track where the alpha particle passed by. To observe these tracks, you can build a glass-enclosed cloud chamber, similar to this one. Inside, the tracks are easy to photograph. They frequently tell interesting stories. Here, for example, is an ion trail photograph showing a pattern of alpha tracks from radioactinium. Here is a similar group of tracks from radioactive polonium. Here you can see what happens when the tracks form in the field of a large electromagnet. The bending of these tracks is due to the interaction of the charge carried by the alpha particles and the magnetic field. It proves that the particles carry positive electric charges. Now suppose the radioactive material you use as the source of alpha rays is itself a gas mixed with the air. In this case, the spontaneous explosions which eject the rays can start anywhere in the chamber and may move in any direction. Here is a single track from an atom of radon in such a chamber. In the case of thoron, another radioactive gas, the explosions occur in pairs in rapid succession. Hence, we observe pairs of trails diverging from a common point. Let me inject a little thoron into this cloud chamber. At first, you see a cloud formed by confusion of ions as the gas enters. Then, as the gas distributes itself out a bit, you can see pairs of tracks. Each pair of ion trails is automatically transformed into a pair of water drop trails, sharply defined at first and then slowly fading. And now, if you still have a lingering skepticism about the reality of atoms and molecules, you might ask yourself the question, what are those tracks? What makes the Geiger counter click? How can such effects occur if matter is not composed of atoms?
Professor Campbell has left us with a question. Did he do it just for rhetorical effect? I don't think so. I believe he really wanted you to decide whether you wanted to call atoms and molecules and ions real or not. Here's what I would say in reply to his question. I take it that you and I and Professor Campbell think that apples are real. Now, an apple is at a certain place there in space. It occupies a certain volume and it has weight. What Professor Campbell has told you about molecules and atoms shows that they are in these three respects just like apples. Well, not exactly so, but very, very nearly so. So I would say that molecules and atoms are as real as apples. And that goes for ions too. By the way, if you were to deny that apples are real, that would simply move the discussion to another plane. But on that plane, we should still hold the same view of atoms as of apples, I believe. In the cloud chamber pictures which Professor Campbell showed us, we saw tracks being made, which consisted of illuminated water droplets. They were very much like the luminous tracks made at night by a tracer bullet, or by a meteor, a shooting star penetrating our atmosphere. So, seeing this, we say that some kind of small object, which someone thought of calling an alpha particle, behaves like a tracer bullet. We can collect many of these particles, and we find that what we've got is helium gas. So then we say these particles are constituents of helium gas, that is, helium atoms. Moreover, they must be electrically charged in order to be moving on curved tracks in the cloud chamber, as we have seen. Hence they are, speaking more correctly, helium ions. Gas molecules are real because we can find out how many they are in a cubic inch, how fast they fly, and so forth. Atoms are real because we can not only count them off, we can locate them in space as they build up a crystal lattice, like these. Alpha particles are real because they behave like little bullets. These three classes of things, molecules, atoms, and ions, are really small chunks of matter, sometimes electrified, sometimes not, and differing from other chunks of matter, such as apples, simply in being so very, very much smaller. So my own answer to Professor Campbell's question, which I give you for what it's worth, is if apples are real, then atoms are real too. And the same goes for molecules and also for ions. But note that Professor Campbell didn't mention today any other kind of particle. Are electrons real? Maybe they are, maybe they're not. I believe they are. But that poses another question.
What happens in a single community is the problem of its own citizens. But it is also the problem of us all, because as communities go, so goes the nation. A power scale is another important yardstick of despotism. It gauges the citizens' share in making the community's decisions. Communities which concentrate decision-making in a few hands rate low on a power scale and are moving towards despotism. Like France under the Bourbon kings, one of whom said, "The state, I am the state." Today, becomes slanted, its middle income groups grow smaller, and despotism stands a better chance to gain a foothold. Where land is privately owned, one sign of a poorly balanced economy is the concentration of land ownership in the hands of a very small number of people. When farmers lose their farms, they lose their independence. This one can stay on, but not as his own boss anymore. To the extent that this condition exists throughout a nation, the likelihood of despotism is increased. A community rates low on an information scale when the press, radio, and other channels of communication are controlled by only a few people, and when citizens have to accept what they're told. In communities of this kind, despotism stands a good chance. See how a community trains its teachers.
Bear this in mind. Young people cannot be trusted to form their own opinions. This business about open-mindedness is nonsense. It's a waste of time trying to teach students to think for themselves. It's our job to tell them.
And when teachers put such training into practice, despotism stands a good chance.